Hey everybody, today we're taking a look at the beginning of our next chapter. We're going to be talking about in this section, in this video here, tangents and normals. And the idea is that we're basically taking all of the properties that we talked about in the previous chapter when we talked about finding derivatives, and we're now going to be thinking about how that applies to the graphs. So when we talk about tangents, we know the tangent curve or the tangent function of a function is its derivative. And today we're also going to be taking that and talking also about normals as well, which we've talked about previously. Our objectives, we're going to find a normal line to a function using a derivative property and find key information about functions based on the derivatives. So a lot of examples here in this section, but like I said, we're focusing on application of these derivative properties in different types of functions. Now, if you look over here, we have a function y equals f of x, and it's doing whatever it is. But we're focused here right on point A. And if we talk about the tangent line at that point, this guy right here, that's the tangent or the derivative function, which has a slope or gradient m sub t, the slope of the tangent line. But we could also talk about the normal line to that, and it's just a line that's going to come to a right angle there. We refer to that point A as the point of contact because that's the point where the tangent line meets the curve f of x. So we already know how to find the slope of the tangent line. The slope of the tangent line is just the derivative. But we also want to be thinking about the gradient of the normal line, or the slope of the normal line. Well, that's just going to take the notation m sub n for the slope of the normal line. And it's just going to take this equation right here, which reads -1 over the derivative at point A. But you could just remember that that's just the negative reciprocal of the slope of the tangent line. So we're basically taking some algebra properties that we're all pretty well versed with and going ahead and doing some problems with that. So if we look at this example here, we see we have a function x squared. Obviously, the derivative function is 2x. If we were looking for the normal line at x equals 2, well, we could find the slope of the tangent line by plugging in x equals 2 and getting a slope of 4. Well, if the slope of the tangent line is 4, then that means that the slope of the normal line is -1 over that value, or -1/4. So once we have that information, then we can just go ahead and find the y-intercept. Now you see, well, we see two things here. First, this is going to be the slope of the tangent line. Sorry about that. We're using point slope form in this case to find the slope, to find the y-intercept. But you don't have to. You could just go right to slope-intercept form of a line. I think we're all pretty good with that. We don't need to spend too much time with that. Let's just look at this one here, the normal line. If we were to use slope-intercept form, we would say, okay, we know the formula line is y equals ax plus b. We know that we have a slope of -1/4. And the point that we're going to be referencing is the point x equals 2. And when x equals 2, y equals 4. So I can go ahead and plug in 4 equals -1/4 times 2 plus b. And just do some simple algebra there and end up getting their 9/2. So then we can just plug in and get y equals -1/4 x plus 9/2. So again, just really using calculus ideas, but really we're just doing algebra here. So let's look at some examples. Like I said, we have a lot of examples in this video to go through. So it says, find the equation of the tangent line, not the normal, just the tangent line, of this function at the point x equals 1. Well, when x equals 1, y equals, just by plugging it in there, we can see that y equals 2. All right, that's helpful to us. So we can go ahead and start to do some work. Now, what we want to do is we want to find the derivative function, which is just 2x. And then if we're looking for f prime of 1, that'll be the slope of the tangent line at x equals 1. That's going to be 2. So now we can go to y equals ax plus b to find the equation of the line of the tangent and just take what we know. So we know when y equals 2 from right there, the slope is going to be 2. The x value from right there is 1. And we solve for b. Well, b equals 0 there. So we have the y-intercept. We have the slope. Just plug it in. Y equals 2x plus 0. We're obviously just 2x. And if we were to look at that function from a graphical point of view, we could see that yes, in fact, it does have a y-intercept of 0 and a slope of 2. Okay? Starts out pretty easy. Not that it gets tremendously hard, but obviously it'll get a little bit harder as we go on through here. All right, so looking at example 2 here. Now we're looking for the equation of the normal. That's the only thing that's going to change, like I said, is just we're going to have to take the negative reciprocal of the slope, which is the derivative at that point. Now the point that we're referencing here is x equals 4 for this function here. When you plug x equals 4 into the equation there, you end up also getting y equals 4 as well. That's shown right there. And we can just, and again, that's referred to as the point of contact. It's where the tangent line or the normal line, where it crosses our function y, or f of x. So we're going to go ahead and find the derivative function. We're going to find f prime of x. Now, if I think of 8 over rad x, as we see right here, I could also look at that as 8 times x to the negative 1/2. And sometimes that makes it easier on us to find the derivative. That's just going to be negative 4 x to the negative 3/2, or negative 4 over x rad x. And that's helpful because now when I go to find the derivative at 4, I can just plug in 4. Okay, now I have negative 4 over 4 times the square root of 4. And that ends up giving me negative 1/2. But again, that's the slope of the tangent line. If I'm looking for the slope of the normal line, I need to do negative 1 over negative 1/2, which is just going to be 2. All right? So I have a slope. Now I need a y-intercept. So I take my y value, 4, equals the slope, 2, times the x value, 4, plus b. And b equals negative 4. So I have my slope. I have my equation. Y equals slope is 2, x minus 4. And again, we can take a look at the graph and see that is in fact what we have going on here. We see the function, and then we see the tangent line right there, and then we see the normal line going through right there, meeting at that 90-degree angle that we talked about. All right. So next one is find the equation of any horizontal tangent to this function right here. Well, if it's a horizontal tangent, then what that tells us is that the derivative at that point is going to be 0. So let's go ahead and start by finding the derivative function. That's just going to be 3x squared minus 12. We want to know when the derivative equals 0. So I'm just going to solve this. Okay? So I'll pull out a 3, and now I have x squared minus 4. Obviously, that means that x squared equals plus or minus 2. Now, those are the x values. But that's not going to be the equation of a horizontal tangent. The equation of the horizontal tangent is going to be y equals some number. So what I need to do is when x equals negative 2, I need to know what y equals. And when x equals positive 2, what does y equal there? And what that's going to do is it's going to find for us the points on the function. And then whatever that y value is, that's what the equation of the horizontal tangent is going to be. So if I were to take this negative 2 and plug it in there, I end up getting, let's see, negative 14. And when I take that positive 2 and plug it in there, I end up getting y equals 18. Okay? So that means that my equations of horizontal tangents are these two equations. They're not a point there. It's y equals negative 14 and y equals positive 18. And if you look at it from the graphing calculator, you can see here we have the y equals 18, and here we have the y equals negative 14. Or maybe I said them backwards, but whatever, you get the point. No, they have negative 14 there on that point. Okay? Okay. Example 4. All right. Show that the equation of the tangent to y equals a natural log of x at a point when y equals 1 is this function here. Okay, so show that. This is a tangent, not a normal. It's important to keep track of what's going on here. Now, when we have y equals the natural log of x, but what they're telling us is that y is negative 1. I'm starting to think of some relationships that might be going on here. When is the natural log of x going to be equal to negative 1? You might be thinking about an e, and it's some approach to an e. If I took negative 1 times the natural log of e, that would work. But obviously, that's not exactly what we're looking for. But just through some simple manipulations, I could just use a log rule and say that's e to the negative 1. Therefore, x equals e to the negative 1, or 1 over x. Right? You could obviously do some calculator work to find that as well. But just kind of that conceptual understanding is pretty helpful as well. Okay, so again, we're talking about the slope of the tangent line. So we're going to start by finding f prime of x, the first derivative. And it's a simple one, and that's just 1 over x. But what we're looking for, f prime of 1, oops, that should have been over here, 1 over e. So we are really just plugging in f prime of 1 over e. So that's the 1 over e, which is just e. Okay, so that means that's the slope. All right, so we know here this is our slope. Now we need the y-intercept. So we're going to say y value, negative 1, equals the slope e times the x value, which we found over here to be 1 over e plus b. All right, so we could just do some simple math there, and we end up getting this here. This part just becomes 1. So b ends up being negative 2. So our equation is y equals e x minus 2. We've shown that they're equal to each other. Going through a lot of examples. All right. Next one, number 5. Slope of the tangent again. So we don't have to worry about the negative reciprocal. And it says slope of the tangent for the function y equals tan x. And here we are, x equals pi over 4. Well, if x equals pi over 4, let's go ahead and start out with that for a second. Here we are at pi over 4. We know that we have rad 2 over 2 for the vertical component, rad 2 over 2 for the horizontal component, and we know that tangent is going to be the same as the sine over the cosine. So it's rad 2 over 2 over rad 2 over 2. That's going to give us a y value of 1. Now that we have that, we can start to do some more work here. So let's go ahead and start with the derivative function. The derivative of tan x is one that we've studied previously. That's just going to be secant squared x, or 1 over cosine squared x. So when we go to find f prime of pi over 4, that's just going to be 1 over, we have the horizontal component right here that we can just go ahead and plug in. Rad 2 over 2 quantity squared, which is just going to give us 2. Okay, so that's, again, that's our slope of our tangent line. Now we're going to need to find the y-intercept. So we're going to plug in the y equals a x plus b. Sorry about that. Okay. So we have 1 equals the slope times the x, which is pi over 4, plus b. And with that, we end up getting b equals 1 minus pi over 2. So the slope of the tangent line is going to be y equals the slope, which is 2, x plus 1 minus pi over 2. Right. A lot of algebra. And you're going to see that for the most part in this whole chapter, nothing really new, just really kind of focusing on some graphical analysis of these derivatives and what they mean, building our repertoire of why we take derivatives and why we learn calculus. Next example, example 6. This is our last example for this section here. We're looking for the tangent of this function at 1, 4. And we want to know when it's going to meet the curve again, all right? And that might sound confusing, but as we go through, we'll kind of build an understanding of what's really happening in this particular problem. So let's just go ahead and start with finding the derivative. The derivative function is 3x squared plus 1. Now what we're looking for is the slope of the tangent line when x equals 1. So I'm looking for f prime of 1. That's just going to be 3 times 1 squared plus 1, or 4. Now, the equation of the tangent line, so again, just kind of keeping track, this is the slope of the tangent line. And now I want the equation of the tangent line. So I'm going to say y, which is 4, equals the slope 4 times the x value 1, and that's just again coming from up there. And I'm going to say plus b, and b ends up being 0. So now I have my y-intercept of the tangent. So I have the equation of y equals 4x. I could say plus 0, but I don't even need to say the plus 0 part there. Okay. Now, here's where I'm going to show you the graph. So what we have are two functions here. We have this function here. That's the original function, x cubed plus x plus 2. And then we have this point right here, which is the 1, 4 that we're referencing. And when we say the tangent line, we're talking about this line right here. And you can see that it touches only once right here at the point of contact 1, 4, but it also touches down here. And that's what we're looking for. We're looking for that point of intersection. Now at this point, we could do some algebra to figure this out, but the easiest thing is just say, okay, I'm going to take my tangent line, y equals 4x, plug that into y sub 1 in my calculator, and then take the original function, x cubed plus x plus 2, put that in y sub 2, and then use my calculator to find the point of intersection. And when you do, you end up getting that point of intersection being -2, -8. We've all done that many times, so I'm not going to take the time to do that at this point. So what we did was we spent a lot of time talking about normal lines and tangent lines and how to find them for different kinds of functions, and then basically what it means and what the graphical understanding of what's going on there. So that's it for this video. We're going to continue talking about tangent lines and what it means for the graphs and things like that moving forward. That's it. Have a good day.